Welcome to Lecture 6, R.6, Rational Expressions and More Operations on Radicals. So a rational expression, basically in the word rational, we see the word ratio, which is the same word or type of meaning for a fraction, like a half or something. And then radicals we've looked at before. So, for the first objective, we have determine restricted values for a rational expression. So what does restricted mean for rational expressions? Well, in general, the word restricted means something you're not allowed to have, right? So for math problems, sometimes you might be able to put a number into the problem that would make the problem undefined. Undefined means, well, there's no definition for it. So we want to avoid things that we don't know how to define. All right, so that's what we're trying to do. We're going to look at these and figure out what values that we need to restrict. All right, so what is one thing we know about fractions? There's this one thing that we know about fractions that you can never do. For example, if you had, let me take that back. If you had a number, let's say 1 over 2, this is okay, right? You can divide a number by 2. How about if you divided it by 5? Or if you divided it by a negative number, that's fine. Also, you're allowed to have positives on the top or negatives on the top. But there's one number that we should not have in a fraction, and we should not have it in the denominator. And hopefully you've heard about this before, but if you haven't, here we go. So you're not allowed to have 0 in the denominator. No. Okay, that's not defined. Mathematicians, we haven't defined it based on the meaning of what division is. So we're not allowed to have 0 in the denominator. That's what we know about fractions. So what we want to do is make sure that for this fraction, for example, I never ever want to put 0 in the denominator. Okay? So what we're going to say is what values x can be. Alright, so in this problem, we know right away x can never equal 0. So what we're going to do on the number line for our answer, every number is acceptable in the denominator, negatives, positives, but there's only one number we cannot allow. And that number, we already said, was 0 for this problem. So x cannot be 0. Everything but 0. So let me go ahead and answer this in interval notation. Up to 0, union 0 to infinity. So we take a little skip in our interval, and we avoid the number 0. Okay, so that was that one. That one was relatively easy because the x was already by itself. The problem starts to get a little more challenging, maybe, when we have something like a binomial in the denominator. So for this, if I said x can't equal 0, would I be right? Well, let's see. Remember, my main fear is getting 0 in the denominator, okay? So if I plug in 0 for x, right here, I'll get 0 minus 3. What's 0 minus 3? That's just negative 3. Are we allowed to have negative 3 in the denominator? Yeah, we are. There's nothing wrong with it. So in this case, our restriction is not going to be that x cannot equal 0. What we're trying to do is figure out how to make the denominator not equal 0. So we don't want the denominator to equal 0. All right, let's go ahead and try solve that. We're trying to figure out, we know that this cannot equal 0. That's my denominator, right? Let's go ahead and solve for x. Add 3 to both sides, and we get that x cannot equal 3. All right, this one's a little different than the one before, because instead of just being x, we had a binomial. All right, let's go ahead and graph this. X can be everything but 3. So in our number line, we're going to go ahead and take out 3. And then in my answer for interval notation, we just blip out 3, and we're done. Okay, so let's take a look at the next two. Once again, remember, it's not that x can't equal 0. It's that we don't want our denominator to equal 0. So this can't equal 0. So what we're going to do is find out which number is the problem number, or the problem child, for example. And we're going to take that number out of our answers. And then we don't have a problem anymore. So that's our goal, is to take out the problem number. And to do that, we set the denominator to 0, and we solve for x. Minusing 4 from both sides. 3x cannot equal what? Okay, let's go ahead and divide by 3. So, we have that x cannot equal negative 4 over 3. Why? Because if I plug this into that binomial, I would get 0 in the denominator. Let's check that. Okay, let me go ahead and write that binomial over here. And I want to see, if I plug in negative 4 over 3 for x, do I actually get 0? Let's check that. So plugging in negative 4 over 3 for x, that can go over 1. Okay, so we can cancel the 3's, and then we're just left with negative 4 plus 4, which is 0. Okay, so negative 4 over 3 is the problem number, because it makes my denominator 0. Alright, so we're good. We have checked that. We know we cannot let negative 4 over 3 be a part of my answers. So on our number line, we're going to go ahead. Oh, this is getting squishy. Ew. Wait. Let me rewrite this. Okay, so on our number line, we can't let x equal negative 4 over 3. So go ahead and take that out of our answers, and every other number is fine. So in interval notation, taking out that 4 over 3, and we're done. Ooh, not enough space on this one. Alright, so the last one. It has a typo. Please go ahead and take out that y. That's not supposed to be there. It's just be 5x squared. Okay, so now, remember, as usual, we're trying to figure out what makes this denominator 0, because we don't want it to equal 0. So to figure out what that value is, we're going to go ahead and solve for x. Alright, let's divide both sides by 5. And then we get x squared equals, or cannot equal, 0. And then, so solving for x, we're going to take the square root property, both sides, plus or minus, which actually doesn't matter because there's a 0 there. So we get that x cannot equal 0. Alright, well, in this time, x can't equal 0, even though there's that 5 being multiplied to it. Okay, so once again, we're going to go ahead and take out 0 this time. Alright, and that is it. So, as usual, we're just trying to figure out what makes a denominator equal to 0. When we find that problem number, we take it out of our answer. Alright, so objective 2, simplify rational expressions. So we have this definition here. If we have a fraction of two real numbers, what we can do is multiply, or we can cancel out the same value there, and we'll be left with that fraction. So if there's something that is the same in the top and the bottom, you can cancel them or simplify your fraction. Alright, so that's our plan. We want to simplify. If we can find something in the top and the bottom that we can cancel, we've simplified. Let's look at 3x over 10x. Well, they both have an x. So if we divide, or take out from the top and the bottom x, we're just left with 3 over 10. Now 3 and 10, they don't share any common factors, so we're done. For b, well, you know what? Right now there's still just subtraction problems going on, so first we need to turn these into factors. So to do that, I'm going to go ahead and factor the top and the bottom. That's the difference of squares in the top. Oops, that should not be a square. And then at the bottom, we can factor that to x minus 4, x plus 3. Now let's take a look at these two. Do they have anything in common on the top and the bottom? Well, in the top there's an x minus 4, and in the bottom there's an x minus 4. So we can cancel them out. Notice, though, we could only cancel them after we turned it into a multiplication problem. We couldn't cancel when there's still subtraction going on. Be very, very careful about that. Okay, so we can cancel that. And we're left with x plus 4, x plus 4 times x plus 3. So now you might ask me, well, can we cancel the x's since they're the same? The answer would be no. What is the difference between this one and this one? This problem has multiplication going on. It's the 3 times x and the 10 times x. In the other one, there's the addition. So you cannot cancel over addition. You have to have the multiplication going on to cancel the whole term. Please, please, please keep that in mind. Okay, that is a common error I see, so make sure to avoid making that error. All right, so in the next one, let's see, simplify rational expression. Well, in the bottom, it's just a 4, so we can't really simplify that. But in the top, we have that addition, so we can't cancel anything yet. We can't cancel the 8 and the 4 because the 8 is being added. So what we can do is if we factor something out of the top, maybe we can cancel. Now the 8 and the 2, their greatest common factor is 2. So factoring that out, now we have multiplication in the top. And remember, we can cancel across multiplication. So we can take out a 2 here and take out a 2 here. 4 divided by 2 is 2. So now we're left with 4 plus root 6 divided by 2. Now you might say, can we cancel the 4 and the 2? And the answer is no, because we have that addition. You need to have the multiplication going on right there in order to cancel. All right, and that's it. Let's take a look at D. Once again, we have the subtractions going on, so first we need to create the multiplication in order to see if we can cancel anything. In the top, I'll go ahead and factor out the greatest common factor, which looks like it's going to be 2. 7 minus x. And then the bottom, let's see, we can take out an x. So we have x minus 7. Oh, the top and the bottom, they look so similar, x minus 7 and 7 minus x. But they're not the exact same thing. But I can be sneaky. What I'm going to do is I am going to factor out a negative 1 from here. Let's go ahead and check that on the side. So if I have 7 minus x, and I take out a negative 1, what's left over? Well, imagine if you had to re-multiply in the negative 1, and you wanted to get this. In order to get a positive 7, you would need a negative 7. And in order to get a negative x, you would have needed a positive x. So 7 minus x is the same thing as negative 1 times negative 7 plus x, or negative 1 times x minus 7. Okay, so let's go ahead and rewrite that. That is 2 times negative 1 times x minus 7 divided by x times x minus 7. And now we can see these guys are like terms. They're a common factor. So now we can cancel them because there's multiplication going on. Let me go ahead and erase this work here. And we have 2 times negative 1 divided by x. 2 times negative 1 is negative 2 and divided by x. No other common factors, so we're done. So what some people would have done, instead of doing this long factoring thing I did, they would have noticed these guys are considered opposites of each other. So when they see that, some people do the shortcut, you just cancel and you remember to put the negative 1 on the top instead of writing it into the problem. So some people like to do the shortcut, other people like to write it into the problem. Up to you, but just make sure you remember that negative 1 when you're dealing with opposites. All right, objective 3, multiply and divide rational expressions. So if you have two fractions being multiplied together, what you do, you multiply the top values together, then you multiply the bottom values together. And then if you have a division problem, to simplify it, what you'll do is called a keep, change, flip. Keep the first value, change the sign from division, turn it to multiplication, and lastly, flip the value of the last fraction. And that is how you would start to simplify a division problem, which you would then solve like you had done previously for the multiplication. All right, for example 3, we're going to do as indicated. All right, I see two fractions, and I see a division sign. So what am I going to do? I'm going to keep change flip. Keep the first one. Change the sign, and then flip the other one. Alright, so now we have multiplication problems. So what I want to do first is factor. So factoring the top, let's see what's in common there. They both have a 7, so you can take that out. So that's x minus 1. Then let's factor the bottom. That looks like it factors into x minus y, x plus y. Alright, multiplied by, and factoring the top one, they both share an x, so let's go ahead and take out that x. And then the bottom one, that's not factorable, it's just a monomial. Alright, so now I'll go ahead and multiply across, multiplying the top values, then multiplying the bottoms. So we have 7 times x minus 1, times x minus y, so all multiplication in the top. Then x minus y times x plus y, lastly times the 21x. Alright, so now I've got a fraction with a lot of multiplication going on. I could possibly cancel something. Let's see, are there any terms that are similar? We have an x minus y and an x minus y. Let's cancel those out. And then we have an x and an x. Let's cancel those as well. What else can we cancel? We're in a canceling mood. 7 and 21. They both share 7, so 7 divided by 7 is just 1. 21 divided by 7 is 3. Okay, let's go ahead and see what's left after we've done all of this. So we have x minus 1. Oh, that's it on the top. Divided by 3 times x plus y. And that's it in the bottom. None of the other things can be factored. There are no other like terms. So we'll go ahead and box it. Now you would not multiply back out. Why? The best thing to do is to leave it factored, because it lets the teacher know that most likely you checked to make sure there were no other terms to cancel. If you didn't factor it, I might wonder if you knew that you should be looking for terms to cancel. So best to leave it in factored form. Alright, let's look at objective 4. Add and subtract rational expressions. So, if you have two fractions, and they have the same denominator, notice this is a key point. They need to have the same denominator. Then, keep the denominator and add the numerators. Similar idea for subtraction. If they have the same denominator, very important, we can't have two different denominators. If they have the same denominator, keep the denominator and subtract the numerators. For the next one, let A, B, and C be real valued expressions, or just real numbers, or any monomials, binomials, things like that. Then if you have a fraction, if you times the top and the bottom by the same number, you're good. They're equal. Now this is often called the building up property. This is often used when you're trying to add or subtract fractions. Why? Because you may not always have fractions that have the same denominator. So in order to make the same denominator, you're going to use the building up property. Okay, so what are the steps for adding and subtracting rational expressions? So the first step is to factor the denominators. And find the lowest common denominator. Alright? So I'll go over how to find that. Second step. Use the LCD, or the lowest common denominator, to make the same denominator. Okay, remember, our goal for adding and subtracting fractions is to have the same denominator. And then step 3, add or subtract. Step 4, simplify. Whew, almost forgot how to spell simplify right there. Okay, So, and these steps are explained a little further on page 63 of your textbook if you want to take a look at that. So example 4, do as indicated. Well, what's being indicated? Well, we have two fractions, and we are adding them. So you might be tempted to go ahead, add these two together, add those two together, but pause. For fractions, you need the same denominator. And right now, these guys do not have the same denominator. That's a 4a and that's a 10a squared. We have a problem. Our problem is they don't have the same denominator. So our goal is to get the same denominator. But I mean, what would the same denominator even be? That's where the LCD comes in. The lowest common denominator. So what we want to do is first make sure the denominators are factored, which they are because they're only monomials. And then what we're going to do is just like how we did factoring previously. So let's see. This is a 2 times a 2 times an a. So actually I am factoring it a little bit more. Kind of lied there. So 2 times 5 times a times a. So we factored them. Now let's see. I want to make sure they're all included in the common denominator. So this one has two 2's. So we're going to go ahead and write two 2's in here. It also has one a, so let's go ahead and write one a in. Alright, so this guy's satisfied. He's included in the common denominators. We're good. Now we want to make sure that the other denominator is included. Well, do we have 1, 2 in there? Yeah, we do. Okay, he's happy about that. Do we have a 5 in there? No, we don't. Okay, we need to add a 5 for the other denominator. Alright, how about 2 a's? Do we have 2 a's? No, we only have 1. So we have to add one more a, or multiply in one more a. And now we're good. Okay, so the thing about the common denominator is you're trying to find a way to fit both of your denominators into that expression. So it pretty much is going to be bigger than either one of these. Okay? Because you're trying to fit both of them in. Okay, so my LCD, let me go ahead and simplify that. That's going to be 2 times 2 times 5, so that's 4 times 5, 20. 20a squared is my common denominator. So my goal is to get 20a squared as the denominator for both of these expressions. I can't just write 20a squared, though, because I've changed the problem. So my question is, how can I make 4a look like... Ooh, that's supposed to be a 20a. It's missing a 0. How can you make 4a look like 20a? Well, if I multiply 4 by 5, I get the 20. Okay, I can do that. And if I multiply the a by another a, I get a squared. So I can multiply the top or the bottom by 5a to get the 20a squared. But pause. Remember that rule that we had up above? If you multiply it to the bottom, you need to multiply it to the top. So that's what we have to do. We found out what we needed to multiply to the bottom, and sort of as just an after side effect, we have to multiply it to the top. So on the top, we get 7 times 5a, and the bottom was the 4a times the 5a. So now try to figure out what you need to multiply to the 10a squared to get to 20a squared. All right, so all we need to do is multiply it by 2. But we need to multiply the top by 2 as well. So that'll be 11 times 2. All right, let's simplify this. That's going to be 35a plus 22 divided by 20a squared divided by 20a squared. All right, so now we have the same denominator. Now we can go ahead and add our fractions. So we keep the denominator, and then we add the numerator. So 35a plus 22. Now let's see. If I can factor the top, then I might be able to simplify further. But looking at the top, this is just 7 times 5, and that's 11 times 2. These guys don't have anything in common. So we're actually done. There's nothing else to simplify. We tried to factor, and it didn't factor. All right, so let's go ahead and look at example 5. Do as indicated. Okay, what's being indicated here? It's subtraction. We're trying to subtract two fractions. how do we subtract two fractions? Well, they need to have the same denominator, and right now, these guys aren't the same. So what's our plan? Factor, find LCD. Go ahead and pause the video, try to factor this and find the LCD by yourself. Alright, so factoring these, I get x plus 3, x plus 1, minus x minus 5 over x plus 3, x minus 1. Alright, so these are my two denominators. Now for the LCD, I want to make sure they're both satisfied. So I always just throw the first one right on in. And then I check with the next one to see what else I might need. So I'll go ahead and put that x plus 3, x plus 1. Okay, this one's satisfied. I should put this one's satisfied. Now, for the next denominator, do we have an x plus 3 inside? We do. We're good. Do we have an x minus 1 inside? No, we don't. So we have to make sure everyone is happy. So let's go ahead and put in that x minus 1. Alright, that's my LCD. So our goal is to make each of these look like that by multiplying by something. So what would I multiply this denominator by? Oops, wrong pen. This denominator by to get that. Well, the only thing it's missing is the x minus 1. Let's go ahead and multiply by x minus 1. Alright, so now what is this one missing from here? Well, it's just missing the x plus 1. So let's go ahead and multiply the x plus 1. And remember, we have to multiply to the top. That's the building up rule. Let me go ahead and put these in parentheses. Okay, let's go ahead and take a look at what we have. Whew, a lot of binomials. Alright, well the denominators are the same. Let's go ahead and subtract across the top. X minus 1, 3x plus 5, minus x minus 5, x plus 1. Okay, we're nearing the finish line. The problem is, I still have this subtraction in the top that I need to do. And in order to do that, I actually have to multiply these guys out. Alright, we're going to go ahead and use FOIL. You can pause the video and try use FOIL to multiply those out. So what do we get when we multiply them out? We have that minus sign from the middle. And we're going to go ahead and make sure we have the parentheses there. So for the first one, for f, we get 3x squared. Outside we get 5x. Inside we get negative 3x. And last we get negative 5. Then for the next binomial, we get x squared minus 5x plus 1x minus 5. And that is all over our LCD, which we are not going to multiply out. Why? Because there is no subtraction problem going on. It's all just multiplication. Alright, so let's simplify this. We can combine those two like terms. And then we can combine the like terms inside the brackets. So we get x squared minus 4x minus 5. Alright, we're getting pretty close. Now let's go ahead and distribute that negative to all of the terms. Minus x squared plus 4x plus 5. Divided by x minus 1, x plus 3, x plus 1. Alright, combining like terms. We have the x squareds, the x's, and the negative 5. Okay, so let's see. Using the x's, we get 2x squared. Adding the x values, we get plus 6x. Lastly, adding the number values, oh, those guys cancel each other out. So we're just left with the 2x squared plus 6x. Let's go ahead and factor that. once we factor it, we can see if we can cancel anything. So let's see, factoring that out, we have 2x, what's left over? X plus 3. Ooh, I'm kind of running into the room on the other problem. Getting a little too squishy here. Do we see any like terms to cancel? I do. I see the x plus 3 and the x plus 3. Let's go ahead and cancel those out. And I'll use my squiggly line to let me know where I'm going with my work. Not the best way, but this will do. 2x over x minus 1 times x plus 1. And once again, we're not going to multiply it out in the bottom because leaving it factors shows me that you checked to see if you could cancel stuff. Alright, and there we go. It was a lot of work, but follow the steps, build up the base, keep the denominator, subtract the exponents. Once you've done the subtraction, you'll get to the final stage here where you can factor it and then do your cancellation. Okay, so let's look at the next problem. Oh, this one is big. Now we have 3 terms. Not only do we have 3 terms, we have subtraction and division. So we have to remember PEMDAS here. And in PEMDAS, division comes first. So we actually have to do this division before we can do the subtraction. Alright, so in order to do division, remember what we do is for division, we actually end up changing it to multiplication. So we do the keep, change, flip. So let's go ahead and do that. I'm going to do the subtraction, and then I'll put parentheses in to show that we're working on the division first. So, working on the division, we'll do keep the first value, change to a multiplication, and then flip the other fraction. X plus 5, x minus 7. Alright, so once we've done that, to simplify the division, we're going to factor. So factoring the bottom, let's see, we get x is 15, that'd be 3 and 5. X plus 3, x plus 5, times x plus 5 over x minus 7. So now that I know that this is going to be multiplied in, I'll just go ahead and cancel out any of the common factors, which is the x plus 5. So once I've canceled that out, I'll go ahead and multiply across. Nothing much there, actually, it's just the x minus 3. And in the denominator, we have x plus 3 times the x minus 7. Alright, and once we've done that, we can actually just drop the parentheses. And now, after we've done with the division, we have a normal subtraction problem, which we've just dealt with. Now, for a subtraction problem, they need to have the same denominator, which they don't. So let's find the common denominator, which we have to make sure that all of them are satisfied, so I'll go ahead, plug them all in. Each denominator is included. So now what we have to do is figure out how to make each denominator look like that. Well, this bigger one over here, it's easy. I'll just go ahead and multiply the 5 and use the building up property, multiply the top by 5. But the one over here, that one's smaller. We're going to have to multiply it by 2 different terms. The 3, the x plus 3, and the x minus 7. To top and bottom, alright, let's go ahead and write this out. Whew. Minus lots of small handwork going on here. As you can see, mistakes could definitely happen because there's lots of little terms to write, so do be careful. Alright, so now I'm going to go ahead and multiply out the numerators. I'm not going to touch the denominators because we leave those factored. Okay, multiplying them out. Let's see, I'll do these guys first. That's going to be x squared minus 4x minus 21, I believe, all over x plus 3, x plus 5, x minus 7, minus. And in the top, multiplying these guys out, that'll be x squared plus 2x minus 8. Oh, 15, not 8. All right, looks good. And then writing down the common denominator again. All right, so now we can go ahead and do our subtraction. Oh, close. We're not done yet. I need to go ahead and multiply in that x first. So multiplying in the x, I would get x cubed minus 4x squared minus 21x. Okay. Now I'll go ahead and put those in. X cubed minus 4x squared minus 21x. And then we have to distribute this negative to all the terms. Please be careful. You need to remember to distribute that negative. Negative x squared minus 2x plus 15. All right, let's go ahead and combine like terms. Here's my arrow to let us know where we're going. Let's see. What terms combine? The x cubed is by itself, but the x squared, we have 2. Then we have 2x values, and then we have one lone 15. Okay, I'll go ahead and write that out. So my LCD and then in my numerator, x cubed didn't have anybody else. And then the 4x, negative 4x squared minus the x squared is going to be negative 5x squared. And then the negative 21x minus 2x is going to be negative 23x. And lastly, the plus 15. All right, let me go ahead and just rewrite this once again, a little neater. All right, so you could try factor at the numerator, but it doesn't actually factor. You can try the grouping. So since it doesn't actually factor, we're going to go ahead, and this is just our answer. All right, so moving along. Example 6, simplify the complex fractions. All right, so complex fraction, what does that mean? Basically, it means a fraction within a fraction, which you can see here. We have the main fraction bar, and in the numerator we have 2 fractions, and in the denominator we have 2 fractions. And we don't like complex fractions, so our goal is to always get rid of complex fractions. To do that, we're going to use the building up property, and we're going to create an LCD. So looking at the mini fraction denominators, what's the LCD? Well, it's going to be 4x. So then I'm going to go ahead and multiply the top and the bottom of the fractions by our LCD of 4x. And I'll expand this to show you what's happening. Once I do that, what I'm going to do is multiply in, or distribute in, that 4x to each of the fractions. So we get x divided by 4 times the 4x, and I'll put it over a 1, minus, that's that minus right there, 4 over x times 4x over 1. Again, I just put it over 1. This is the main division bar, which I have right here. And then we have the 1 over 4, and we distributed in the 4x, which once again I'll put over 1. Then we have the plus sign, and then 1 over x, and I multiply that by the 4x over 1. So remember, our goal is to get rid of the mini fraction. So let's see if we've accomplished this. Let's go ahead and do some cancellation. Well, this 4 cancels with that 4. The x cancels with the x. 4 with the 4, x with the x. What are we left with? So all we're left with here is x times x. So that'll be x squared. And then 4 times 4, which is 16. All over, just an x down there. and a 1 times 4, which is just 4, so plus 4. All right, that's what we're left with. As usual, we want to make sure the top and the bottom are factored and to see if we can cancel anything. The denominator, that is factored, but how about the numerator? That looks like the difference of two squares. Aha, it has popped up again. All right, let's go ahead and factor that, the difference of two squares. X plus 4, x minus 4, all over the denominator of x plus 4. Can we cancel anything? Yes, we can. The x plus 4, sorry. And so we're left with an answer of x minus 4 is our simplified answer. Okay, so we treated a complex fraction pretty similarly to how we treated other fractions by using the building up property. But the thing we used the building up property for was to get rid of the mini fractions. So we were just left with one normal fraction. That's the plan. Okay, let's look at D. Okay, this one looks really weird. Why? We have negative exponents. Now we can't do anything with those negative exponents at the moment, so my plan is to get rid of negative exponents. And how do I do that? Is there a property that can get rid of a negative exponent? Why, yes, there is. It is, as I love to say, the fish underwater. Okay, so we're going to go ahead and use that property. Or fish out of water. Okay, so taking the reciprocal, that's going to be 1 over d to the 1 power, but I'll just leave it as 1 over d. Minus, we'll take the reciprocal of that, 1 over c, divided by, this is the main division line right there, the reciprocal of that, which is 1 over d again, and then the reciprocal of the next one, which is 1 over c. And I brought down both of the minus signs. Okay, so now we have a complex fraction, but we know how to deal with them. Let's find the LCD and use the building up property. So the LCD, looking at all the denominators, the mini denominators, it's going to be CD. Okay, what do we do with that? Well, we multiply it to the top and the bottom with hopes that we can cancel out the mini fractions. Okay, so let's go ahead and rewrite this. So we have 1 over d times the CD, and I'll put it over 1, minus the 1 over c times CD over 1, divided by the 1 over d times CD over 1, minus 1 over c times CD over 1. Phew. Alright, let's go ahead and carry this on over here. Did the mini fractions cancel? Let's see. Well, that d cancels with that. The c cancels with the c. D with the d, and c with the c. Now you might be asking, why am I not canceling these guys together? The reason is that subtraction sign creates sort of a division. So each of these are their own sort of multiplication groups, and you can only cancel within those multiplication groups because of that subtraction. Or it might be a plus sign, but in our case it's subtraction. Alright, let's see what happens after the dust clears. We have a c left over in the numerator, and just a d left over in the other spot, divided by what's left over here, a c, and then a d. And what do you know? C minus d divided by c minus d, those are the same exact things. We can go ahead and cancel those. What are we left with? The answer is 1. Anything divided by itself is 1, and there we go. Alright, so our answer is 1. Let's take a look at E. Okay, so once again, this is a complex fraction. It doesn't look like the other ones we were working with exactly, but there is a mini fraction inside of a fraction. So it does fall into the category of complex fractions. So we're going to use our same plan of using the LCD to cancel the mini fractions. But before I do that, what's the denominator of the 2? It's 1. What's the denominator of the h? It's also 1. Okay, be very careful to add those in. Now let's see, what's the LCD? Well, looking at all the denominators, the only thing we have is the 1 minus h. Alright, so that's going to be my LCD. Let's go ahead and multiply that to the top and the bottom. Let me rewrite this with all the multiplication, because as usual, we're distributing it in. So we have 2 over 1 minus h times the 1 minus h, and we'll put that over 1. Then we bring down the minus sign, minus 2 over 1 times the 1 minus h, which I'll put over 1. And the main division line. And then we have the h over 1 times the 1 minus h over 1. Alright, let's see what cancels. Hopefully the mini fraction cancels. So, in this group, the 1 minus h cancels. In this group, nothing cancels. And nothing cancels in this one. Okay, so try pause the video, see if you can continue working this out. Okay, so hopefully you took a second to try work this out. So let's see what's left over. There's just the 2 there left over. Minus, and then on the other side we have the 2 and the 1 minus h. And in the bottom we have the h times the 1 minus h. Let's go ahead and multiply out the top of the 2, and let's distribute in that negative 2. Minus 2 plus 2h divided by h times 1 minus h. Simplifying the top, the 2's cancel each other out. And we're just left with 2h over h times 1 minus h. As usual, I ask myself, can I cancel anything? Can I simplify? The answer is yes. We have those 2 h's. Canceling out those h's, we're left with 2 over 1 minus h. And we are done. Now let's take a look at the 5th objective. Alright, so the 5th objective. Actually, this is an error. This is the 6th objective. And that should say numerator. The 5th objective was the complex fractions. Okay, so 6th and final objective, rationalizing the numerator or the denominator. So what does that mean, rationalizing the numerator or the denominator? Basically, it means getting rid of a radical, in this case. Okay? So, if I was told, for example, 7, rationalize the denominator, that means I don't want a square root of 3 in the denominator. It could possibly be in the numerator, but I don't want it in the denominator. So how will we get rid of it? Well, what tools do we have in our tool bag for working with fractions? One of them is that wonderful building up property, multiplying the top and bottom by the same thing. We're going to use that once again here. So it's a very useful tool, the building up property. So my goal is to multiply the cube root of 3 by something that makes it not a radical anymore. Is that possible? The answer is yes. Try to take a moment to think on that. What could you multiply cube root of 3 by to get rid of the radical? Well, if I multiply the cube root of 3 times another cube root of 3, I'll get the square root of 3 times 3. Sorry, I said cube root, I mean square root. And then that's going to be the square root of 9. What's the square root of 9? It's 3. Poof! The square root's gone. So, we're going to use that plan here. We're going to multiply to get a perfect square inside our radical, because then that'll cancel with the radical. So multiplying by top and bottom by root 3, we'll get 5 root 3 divided by the square root of 3 times 3, which we know the square root of 3 times 3 is 3 squared. So now I have created that perfect square inside a square root. When I do that, I can cancel. So that was my goal, to create that perfect square inside the square root. And then I am left with 5 root 3 over 3. And voila! There is no more square root in the denominator. We're good. Okay, let's take a look at B. We don't want this in the denominator. And right now, there's a cube root of 4x. So my plan, just like I did above here, I created that square with the square. I want to get something inside the cube root cubed. At the moment, I have a 4x. Well, 4 is actually the same as 2 squared. So we're close. We have a 2. I need a 3. So I want a 2. No, let's see. What can I multiply to 2 squared in x to get a 2 cubed and an x cubed? Because if I had a 2 cubed and an x cubed, then they would perfectly cancel with the cube root. But right now I just have a 2 squared and an x squared. So what can I multiply them by to get that 2 cubed? Well, to get a 2 cubed, you'll just multiply the 2 squared by 2. And you'll multiply the x by x squared. So let's go ahead and do that using the cube root, 2x squared. When I multiply these out, let's see what I get. So y cube root of 2x squared all over. Let's see. So we have the original 2 squared x, and then we're multiplying in the 2 times the x squared. Let's see what I get here. So in the denominator, I'll keep the denominators and add the exponents. So 2 plus 1 is going to be 2 cubed. And then, keeping the denominator and adding the exponents, that's a 1, sorry. That'll be x cubed. Look, I've created my goal inside here. I have a cube. I have 2 perfect cubes inside a cube root. So now I can do the cancellation. So I did multiply my problem by the right values. Okay, so using the cancellation, I'm done. So remember, the goal is to try to multiply whatever you can to the inside so that you can match the radical. All right, that's it for this one. All right, so this next one, there's a really large difference between this one and the other two. And that difference is we have a binomial. There's a minus sign. So the plan is going to change. To get rid of this one, we're going to use the conjugate. The what? The conjugate. Okay? So rationalizing the denominator, what we're going to do is we're going to multiply this by almost the exact same thing, but it should be the conjugate, so there should be a plus sign. You might say, well, why would that help? Well, do you remember, what do we know about conjugates? Conjugates come from the factored form a minus b, a plus b. This equals a squared plus b squared. Sorry, minus b squared. Notice we take the two terms and we square them. So when I do the conjugate, I'm just going to take the two terms and square them. When I square a radical, a square root, the radical disappears. So that's what we're going to do. So 4 times that new 7 plus 5 that I put in. And then denominator, I have the root 7 minus root 5. The conjugate's root 7 plus 5. Now I'll go ahead and use the difference of squares property. Multiplying out the two conjugates in the denominator, I'll end up with root 7 squared minus root 5 squared. That should be root 5. I forgot the root. Okay. Once we've done that, the square cancels with the root. And I'm left with 4 times root 7 plus root 5 all over 7 minus 5. What's 7 minus 5? Well, that is 2. Okay, can we simplify anything? Yes, we can. The 4 and the 2 can cancel, and I'll be left with a 2 there. And finally, I have 2 times root 7 plus root 5. And that's it. Okay, so what did we use here? We used the conjugates. The exact same thing, but the signs are different. And when we do that, we can end up squaring out the radicals. So the radicals get squared out. Alright, so the last example we're going to do is this time we're doing vice versa. Instead of getting the radical out of the denominator and into the numerator, now we're going to take it away from the numerator and possibly put it in the denominator. Plan, rationalize the numerator. Okay, so take a moment to try A by yourself. It's very similar to A from the previous example. Alright, so my plan. I see a square root. I know I want to end up with a value inside that's squared. Once I do that, then I can cancel the radical with that value. Well, at the moment, we have the square root of 9. What do we know about 9? 9 is 3 cubed. Squared, excuse me. So we already have that one square. The only one that doesn't have a square is the x. So how do I remedy that? Well, let's just go ahead and multiply the top by 1x. I have multiplied in the x that I need. So in the top we have 3 squared times x, the original one, and then we'll multiply in that new x that we just added, or multiplied in. And in the bottom we have 2 root x. So in the numerator we get 3 squared x squared, because we kept the base and add the exponents, divided by 2 root x. Now we can go ahead and simplify the square root with the squares. And let me erase my side work here. And this simplifies into 3x all over 2 root x. Can we simplify anything? No, that looks about it. So we're done. Next example. B. Okay, so we're trying to rationalize the numerator, and what I see in the numerator is a 4th root. So this time my plan is I want something inside to the 4th power. Let's take a look at what we have. We have a 2, an x, and a y squared. Nothing's to the 4th power yet. But we can change that. So what should we multiply 2 by to get 2 to the 4th power? We should multiply it by 2 cubed. Then we'll multiply the x by x cubed and the y by y squared. Alright, so we have the 4th root of 2xy squared times, and what was on the inside? We have the 2 cubed, x cubed, y squared. All using just tons of rules of exponents right now. 3x root 2 cubed, x cubed, y squared. Okay, let's go ahead and see. When we simplify this, hopefully we should end up with everything to the 4th power, and then we can cancel with the 4th root. So let's see. Keep the base, add the exponents. Yep, that's 2 to the 4th power. Keep the base, add the exponents. Once again, we get a 4th power. And lastly, the y squares end up with a y to the 4th power. We've done it. Everything is to the 4th power, which is awesome, because now we can go ahead, and after I finish writing down the very long denominator, okay, now we can go ahead and cancel the 4. All those guys get so-called canceled out, and we're left with 2xy all over 3x, the cube root. Oh, that's supposed to be a 4th root. Ooh, I wrote a cube root. For shame. So many numbers, just little things can get lost. It is sad, but it happens. So it's good to check your work. Alright, so 4th root of 2 cubed, which I'll go ahead and rewrite as 8x cubed y squared. Alright, can we simplify anything? Well, the top and the bottom both have an x. Let's cancel that out. And I'm left with 2y all over 3/4 root of 8x cubed y squared. And we are done. Alright, let's take a look at the last example for this section. So now we have that binomial in the top. So we're not going to use the normal method we did up here previously. We're going to use the conjugate method. So go ahead, see if you can use the conjugate method to solve this. Check back in with me in a second. Alright, so the conjugate method, multiplying the top and the bottom by the conjugate, which is going to be the plus, and I get root 13 minus root 10 times root 13 plus root 10 all over 12 times root 13 plus root 10. And in the numerator, because we have those conjugates, we'll go ahead and get the difference of squares. When we take those squares, they'll go ahead and so-called cancel out. And we're left with 3 minus 10 all over 12 times root 13 plus root 10. Continuing on the side, 3 minus 10 is going to be negative 7 all over 12 times root 13 plus root 10. And there is nothing else we can simplify there. I'm just going to go ahead and make sure that that 12 doesn't look like a 72. Make sure your work is clear as possible and legible for the person reading it. And there we go. We're done. So that is it for this section. Please send me an email if you need any help.